Welcome to a new test and teardown video. This time it's the third follow-up video of this mega load. I think I want to call this the remake or a rebirth kind of follow-up sort of way, because I am now redoing everything. New cables, all the transistors been remounted, and my thermal experiments actually did reveal that using more new and fantastic thermal compound, like the one you use in CPUs and all that kind of stuff, that can get you quite a lot of cooler transistors compared to this white old stuff that you're using. I am of course redesigning this, so yeah, see, I've been soldering on top of that. So this is the schematic that I explained about in the end of the previous video. Now I'm going to implement everything and I'm going to reassemble it. As you can see here, all the wires, they have now pre-paired length, so the bottom can go all the way around and up through the holes. That will be the two top modules. There is a little bit to figure out about, see, bottom mounted transistors and the top mounted transistors. So how is this going to realign and all that kind of stuff? But I think I can figure this out. And that will be all the old boards. I'm not going to use those because I want my own little fantastic design instead. It took me only a few seconds to figure out how to assemble this and to actually do it, just because I glued the little isolation discs to the metal end plates. And now it's going to be no big deal if anybody else needs to do service on this in the future, because it's super easy. Nice. So I'm still in the little progress here of assembling everything. I'm really happy about the way the wires goes, and yeah, the edges here of the aluminium heat sinks, those are a little bit sharp, so I sanded it really nice and fine here where the wires go. And I really didn't like the way that it was made previous with these right there, and the wires was just way out and all that. But there is a little point in this little clip here, and that is, I don't know if you remember the clip where I took this apart, where I was crying a lot about the screws and the nuts and the way, see, they go here in this hole, and then there is a nut in there, and you can't really get in there, by the way. But look at that, right next to it, there's a thread in this piece of metal. Thread, hole, open hole, all right? And it's the same, this repeats all over the place. And then those guys that made this one, they insisted on making a hole for the screws. So you need to have a loose screw and a loose nut in that hole where you can't reach in. I mean, all they had to do was figure out, oh, there's a thread. This is going to be easy. Let's do it easy. I mean, hello guys. And this is, yeah, this is just my 5 seconds of wisdom you can take with you. I mean, think about stuff like that. So it's super easy, right? So now I'm done with all the mechanics. Now all I need to do is play a little bit with the electronics. So here is the original controller board. And as you remember, this is ground and we had the resistors in the positive. So my idea is, let's just remove all the components from the board and flip it the other way around. So now the resistors, they will stay in, this will be ground, and now there are emitter resistors, and positive again goes to the collectors, and now emitters. So I just flipped it a little bit around, and I should be able to fit in a little op amp. Maybe I will keep the socket for the optocoupler, because I kind of like that feature. So far I just keep it and see if I can use this space up there for my new op amp. And that is more or less all there is to it. Remember, my schematic is like that, super simple. So it should be something I can just hammer in here somewhere, right? So after I removed all the components, I also removed all the tracks I don't need, because I want to be able to use the same holes and just stick some components through and just pull my own wires left and right and stuff like that. See if I can make it a little bit smart. See, I use acetone, by the way. It's super easy to clean off old solder. See all this, how nasty it was. So now it's nice and beautiful, and I can start my little remake. Oh yeah, by the way, I totally love, this is a Mini Mount. Well, Mini Mount is a brand, but this is a copy of it. I just got so much of that in different sizes and all that kind of stuff. I really like it, and it's super good for prototyping and building up all sorts of super fast mock-ups of whatever kind of test stuff or modifications on top of, yeah, super smart. After a couple of hours, maybe a little bit more than just a few hours, I tried to do it as nice as I could possibly do, reusing all the different holes, and I drilled a little bit of extra holes, and I think I managed to get everything nicely onto this circuit board. So this is my new op amp, and yeah, this is the circuit in case you want to see the back side. It looks a little bit like this. Oh yeah, there's a little extra trick with this, what I've done here. If you look under the op amp socket, you'll see a 10 microfarad ceramic capacitor. So I really added a nice local decoupling there. I also used SMD capacitors here between 1 and 2. That is a 1 microfarad ceramic, and also between 3 and 4. So that is the set point voltage and ground. So yeah, I try to make it real nice. I'm also using the same op amp, the same input components there. I added a little solder joint easy access there with just a 10K resistor. This is just for easy mechanical interface to the solder points here. And now I'll try and mount it inside the case here. I will just test one first and see if it works. I think I'm gonna go all the way with this unit. So now all my 4 circuit boards, they are in and pre-tested, and everything seems to be pretty good. Fine here. And now it is the front. I wasn't really happy about the potentiometers and switches and all that kind of stuff. See? They drilled some wrong holes and all that here. And the range switches for the amp meters, you need to hold it down and all that. I don't like that either. And they were completely corroded. And the front, see, that's actually corrosion marks. Not so nice. And my BNC connectors, they were the non-isolated type. So that means the remote control input, they're also shorted together. I want all my 4 inputs to be completely individual. So I'm going to change these to isolated BNC. And I want, of course, multi-turn potentiometers like this. And I want to verify my meters. They are super duper nice and accurate. So I'm going to pull out everything, clean this up, and see if I can make it real pretty again as well. After a little sanding, and you see, I also re-sprayed it. That's quite nice here, but I got a little bit of dents that's not coming off completely. And also, I'm not so happy about all those extra holes. I only want 1 potentiometer per output. So I think I'm gonna try and blank those holes. My idea is to put some tape on the back and fill it up with epoxy. But first I want to sink the holes a little bit from both sides, so I get more glue surface, and so that this little epoxy glue in is going to stick a little bit better. First I cleaned the holes, but yeah, I think I will try and drill a little bit and see, and then we're gonna try and play with some epoxy. So this is what I mean. I think this is gonna work a little bit better. Now we have a lot more glue surface. I'm using the strongest epoxy you can get, the Ultra. And I'm adding a little bit too much. So there's something you can sand. And also I think it kind of shrinks a little bit when it cures. I'm not so super sure about that. But now I'll have to wait. So after the epoxy is super duper dry, I took a piece of wood with sandpaper on and just moved. It's completely flat and perfect around the holes. How nice is that, huh? Even the big one here. Totally gone. What I want to do is one last little detail around the holes. Of course, I also sanded it on the back side. I take some pieces of glass fiber here. So now I will epoxy here and I'll stick them here on the back. So now I get a perfect seal of my little cover-up repair here. Don't you think that is going to be a fantastic trick? As a part of my refurbish project, I was of course a little bit sad about the way the meters worked in the previous version. It was very inaccurate, and it turns out that this is a 1 milliamp meter, and what I've done is I got here a 10k resistor, and I'm measuring the voltage over the resistor with my voltmeter like that. So I believe this is about 9.9 of a milliamp, right? So this should be this 0.9 line. So let's see if I have now the camera exactly in the middle, and this meter here is perfectly aligned for the picture. And then I disconnect here, and what I want to show is that the line here is now exactly at 0. I have adjusted this little screw here to make this exactly 0, and now when I give this exactly 0.9 of a milliamp, it shows exactly 0.9 here. So that is fantastic. So let's try 0.8, 0.7, 0.6. So, and all the meters, they are this accurate. Oh, now I need to go fine tune my volt, my power supply, right? So to fine adjust 0.4, 0.3, 0.2, and 0.1, and then again I need to super fine tune. The reason why I need to fine tune here for 0.1, that is of course there is a series resistance of about 81 ohms in the meter. So when I go down here in voltage from my DC supply, and also I got some leakage in my voltmeter, this is how I am sure that I have exactly the right current through the meter. So now I can go and figure out how to do the correct series resistors for my meters and my two current ranges. So after I verified the meters are actually super accurate and nice, it really drove me nuts that it's reading milliamps. I mean 0 to 1 milliamp, and we have a 5 or 20 amp full scale. So what I did is I took the original scale out, put it in my 600 dpi scanner, and then I used a little graphic trick to draw myself some new scales like that. See, I even made the little readout lines here a little fatter, and the numbers a little bit bigger and fatter also, and that will be the marks for the two screw holes. So all I have to do now is cut these out and glue them to the back side. And see, if you look through the holes, I don't know if I can show this. If I look through the holes, I mean, it should be perfectly fine. I got an idea about how to glue this to the back side of this little thing. And my idea is to take a needle and press a tiny little hole exactly where the crosses are here. And then I should probably be able to add some glue to the back side, put it here, and still see exactly where the holes are here. And at least this is what I want to try and see if that can work. So this is my very first attempt. Try and see if I got a good glue stick. Try and clean my glue stick on some other paper here. See, now it is nice and fine. See, I made two little dots here. I don't know how much I need. So while it is nice and wet, I'm going to see if I can can I really pull this off? Yeah, I could easily see what I'm doing here through the holes. Look how accurate that is possible to hit that place correctly. How nice. Yeah, I think I'll just see, push it a little bit like that, and I think I'll just let it dry here until tomorrow, and then I will try and cut it out real nice and beautiful. That is my idea about how to do that. So I am now in the assembly process, and as you can see here, I'm going for isolated BNC connectors for the disable optocouplers, because I want those to go individual places and I don't want to create a new ground loop. So obviously you want these isolated. And I think it went all right with the hidden hole. See, if I find the right angle of light, it is actually visible where the holes were, but in real life you can't really see them. It's just because the camera is super crazy sensitive to pick up light reflection differences, and that is what it really is. So yeah, about my meters, look how beautiful that is. And I think this is one of the first times for me to make a complete new nice scale in this kind of quality level here, and I'm so excited about this. So my whole idea with my meter switch, I'm using a two pole switch, and I want to use them in parallel, and I want individual resistors for the two calibration resistors. This way I can calibrate one range without affecting the other range, so it's completely individual. And of course I want the switch to be down, then it's 5 amp, and up it's 20 amp full range. So that is my idea. So here is how I figured out how to do the meter scale calibration. So first, remember a few clips ago, I showed the meter is about 81 ohms and it is 1 milliamp full scale. So I just used LT Spice to put in all the resistors, the 4 emitter resistors, that is 1 to R4. And then I got, of course, my 4 sum resistors. And that is, of course, because you never know if there is a difference in, of course, the 4 emitter resistors or the 4 transistors. This way, there will be a little bit more current in one or more of the emitter resistors, but I want the sum of the current, like my total current, to be visible on my meter. And this is why it was super easy for me just to put in everything in LT Spice, because why calculate when you can simulate? So this is so much easier And then I just figure out the two different resistor values. For R9, that is my calibration resistor. So it's either 415 ohms, that will give me a 20 amp full scale, or 41 ohm, that will give me 5 amp full scale. It is that easy. So I'm ready to do the final assembly. All circuit boards, they are in here, and I did add my sum resistors, so that will be the 0.1 ohm, this emitter resistors, and I'm of course also using the emitter resistors as my current sense resistors. So I got the 10 ohm here and here. That will be the sense point, so using a sum system, and that will be my 20 amp and 5 amp ranges. Let's show you what I've done here on the back. Individual calibration resistors for the two ranges. That means it's going to be so much easier to calibrate all this. And all I have to do is one little final assembly with the wires. There's a small little funny detail, because I want to poke around with all the wires and stuff like that. And you can probably imagine sitting here holding this, you know, all this and wires and whatnot. I mean, look what I did. A little 3D printed part. This one here. I didn't print it beautiful or anything like that. It's not... I don't want to keep this part, but this is only to push in here. Oops. So the idea is I push this. Why is that difficult? Or what the heck is that? See, it should fit like that, right? And then the idea is I take my front plate like that, and see, then it should fit in here, and then go in, see, clickety click, and then see, it will now hold everything like this. Now it should be so easy to handle all the wiring, making it all fantastic. And just bend it down and take these and or throw them away, right? See? Easy, easy. 3D printed parts help your everyday work. Maybe I should show you the little design. What I've done here just in 2 seconds, just a few little video picture clips, just so you can see. I mean, it takes a few seconds to do a design like this. It is that simple. And then the 3D printer will do this in a few minutes. And then, I mean, why not make your life easy? So I was done with this fantastic load, and I started to beat it up and give it a little bit of watts and abuse. And of course I blew up everything here. I tried to see if I could pull off 100 watts per transistor. That is not possible. And they are rated 200 watts, but that is at 25 Celsius. And I am using electrical isolation and not direct mounting. And there's a huge difference. I just tried another one here and tried with or without and do some compares, and it's just amazing. There's a huge difference. So what I want now is I want to redo everything. I will take advantage of the isolated heat sinks. So I will have a primary input voltage, that is the collectors, directly on each heatsink. That is a little bit annoying, but it's definitely the way to go if you want to pull off a lot of watts per transistor. And yeah, so here's my little test setup, just testing real fast, just some thermal properties. I also managed to calibrate all the different amp meters, see, with individual calibration resistors on top of the other resistors. So I went for 47 and 470 ohms. So I knew that I would have a quite a little bit of like 10% or something like that, to little readout in both of the ranges, and then I added some other resistors on top, and now those added resistors, they're quite high, and that gives me a super high good resolution for my calibrations. And it's also quite funny to see that I need different resistors added to get to the accurate readout results. So now all my meters read out as accurate as you can imagine, and it's just a super pleasure to to work with this. Yeah, just too bad I need to change all the transistor mountings. Oh, that sucks, to be honest. There's also a other little detail I want to share you, what I realized when I was doing the meter calibrations. There is actually a visible readout difference depending if the meter is standing up like this and doing the calibrations, changing resistors and stuff like that, instead of lying down like this. And this is how it's going to be used. So when I realized that, of course, I calibrated everything lying down, so I will now have the exact accurate readout when the meter is mounted in the correct position. So this could be a little problem that you need to look into. Of course, a good quality meter with correctly balanced needles and readouts and all that kind of stuff, it should not matter at all. But these are quite tiny and quite cheap, so probably they are not balanced as perfect as they could. I also tried my remote inputs, and it's really cool to find the exact point where the optocoupler works. It's about 1.2 volts. That is the center point, and then I can put in a few volts, a few hundred millivolts more or less, and then I can actually control the whole readout using an external analog voltage. So not just on or off, but there is a nice area where it goes from maximum to minimum depending on where you are, right? So you could remote control this as well, or control the slew rate where you want to, how fast you want to enable or disable your outputs. There's actually also another thing you can do, because I got 4 inputs. So I could put it for 1, 2, 4, 8 amps, for example, and then digitally control this from 0 to 15. That is a super cool idea that I'm having. I don't want to show you so much more. I probably want to put in the schematic here at the end of the video so you can see what I have done and how this is made. And I really want you to think really careful about the transistors you pick for a project like this, and be within the safe operating area. Don't overdrive your transistors with too much power, and be sure about the thermal properties, and then you're going to be absolutely fine. Thank you very much for watching. Please like, subscribe, tell your friends and all that kind of stuff. Bye bye.